Okay, so welcome then today to the plane curves class. We had in the last lecture introduced the projective space and projective varieties. And just to quickly recall how that worked, so we said for a natural number, the n was, so the quickest way to define the projective space was the vector space k to the n plus 1 of dimension 1 higher over a fixed ground field, take out the 0 and mod out an equivalence relation, which is the common multiplication of all coordinates with a scalar. So it means that x0 up to xn is equivalent to x0 prime up to xn prime, if and only if xi prime is lambda xi for all I, and some lambda which is in k without 0. And so that is the projective space, so the set of all lines through the origin. And we saw that if we have in these coordinates x0 up to xn, where the elements we denoted with colons, so that was x0 colons xn, and called these xi the homogeneous coordinates. If we have a homogeneous polynomial in these coordinates, then there is a well-defined zero locus. It's not a well-defined function, but the zero locus is well-defined. So we said that if we have S a subset of homogeneous polynomials, then there is a well-defined zero locus. And as in the affine case, we denote this by V of S. So this was all P and Pn, such that f of P is 0 for all f and s for all the given polynomials. And in our case, of course, we will usually have one polynomial only in then 3 variables, which we will then call x, y, and z, and the standard notation would probably be that this x0, so the additional coordinate would be z, and then x1 and x2 are x and y. So, say in what follows, we have the case usually n equals 2, and then the coordinates will be called x, y, z. Where the c, so the last coordinate somehow plays the role of x0, so the line at infinity, or the hyperplane at infinity. So that's what we did last time, and now we want to come actually to curves, to define curves. And as in the affine case, so a lot of the things today will be analogous to the affine case. We don't want to define a curve as a subset of P2, but rather as polynomials modulo scalars, as this carries more information. And the only thing we see is that we need homogeneous polynomials for that. And hence the definition, as one would probably expect, of projective curves is that we take homogeneous polynomials modulo common scalars. So that means we say that a projective plane algebraic curve, or often we'll just say curve or projective curve, is now a non-constant, to avoid trivial cases calling them curves, is a non-constant homogeneous polynomial f, capital F, usually written as usual, now in 3 variables x, y, z as above, and then again modulo units. So that means modulo multiplication with scalars, just in the affine case. And so they will probably be the main object of study here. So the projective curves are a lot nicer than the affine ones. So usually we will have projective curves in our settings. So a lot of the notations that we had just carry over. For example, we have the degree of curves. So that's obviously here the same. We have homogeneous polynomials. They have a degree. So the degree of such a curve, so denoted as usual, deg f is just the degree of the polynomial, and as in the affine case, we use the same notation. So for degree 1, we will call this a line, for 2 a conic, and for 3 a cubic, and so on. So if the degree of f is 1, we will call this a line. For 2, it will be a conic. And for 3, it's called like cubic and so on. And there's one special line, namely the one line at infinity that consists of all the points at infinity that are not in the affine part. With this choice of coordinates, it will be given by the zero locus of z, and so hence we denote, so we call z like as a curve, as a polynomial of degree 1, the line at infinity. So these are the additional points that we have in contrast to the affine case. And finally, the notions of being irreducible or reducible or reduced or components and their multiplicities are just the same as in the affine case, meaning that you take the irreducible decomposition of this capital F, and then we have the components, and if there's only one, you would call it reducible. And if all the multiplicities of the components are 1, you would call it reduced. So I'll just say the notions irreducible or reducible and reduced, and components and their multiplicities are defined as in the affine case. So by just applying it to the same, by applying exactly these notions to the polynomials, they will be defined to be the corresponding properties of the curves. So that's the obvious definition. And what we want to do is just to relate, of course, these projective curves to the affine ones. And there's various ways to do that, but let's start with some of them. So relations of projective to affine curves. Will be as follows. So there's a way, of course, to go from projective space to the affine part, vice versa. And on the level of polynomials, that is given by a homogenization or dehomogenization of polynomials. And that works as follows. So I'll just do it for the 2 or 3 variables case. So you could do it for any number of variables, would be pretty much the same if you only need it in that case. So let's just start with part A, and the direction may be of homogenization. So say let f be a polynomial in 2 variables, which we call x, y, be a non-zero polynomial of degree d, needn't be homogeneous. Then we define the homogenization by adding another variable to the polynomial such that each term becomes homogeneous. So we define the homogenization of f to be, I think I denote it with little f because I think of it as polynomials and not as curves at the moment, but you could write capital F as well. So I'll denote it by f upper h, so h for homogeneous. And that would be, let's start with f. So it would be like the sum over a, I, j, x to the I, y to the j, where I plus j is less than or equal to d, as the degree is d. And the degree d term, any degree d term will, some degree d term will occur. Then we'll write f upper h for the polynomial in 3 variables, which is just given by x to the I, y to the j, and then adding another variable z with such an exponent so that the total degree becomes d, which is here d minus I minus j. So again, it's the same sum, I plus j is less than or equal to d. And so that will be a homogeneous polynomial. It is now obviously of degree d, and it doesn't contain the z as a component, the line at infinity, because the original polynomial was of degree d. So there's at least one term where this number here is 0. So that means that does not contain z. So this is a homogeneous polynomial. polynomial of degree d that let me write it that way. So with z is not a factor, so z doesn't divide fh, because there was at least one term that was of degree d, and hence that doesn't contain z at the end. So this is called the homogenization, and there's a similar operation the other way around. So let's again call maybe f in x, y, k, x, y, z now a homogeneous polynomial. Then you can make it inhomogeneous by just setting the last variable z to 1. Let this be non-zero and homogeneous of degree d. And so it would have a representation as a sum over I and j and k, where the sum of them is now always equal to d, and then some coefficients a, I, j, k, x to the I and y to the j, d to the d. So that's the general form of a homogeneous polynomial. Then we define the dehomogenization of f to be, so that we call f, or I called it fi for inhomogeneous, and that would be given by, I mean, could you write it as a formula by saying this is f at z equals 1, or in other words, it's the same sum as above, so I plus j plus k equals d, and then we have the same coefficients a, I, j, k, and we just leave out the last variable, so it's x, I, y to the j. So that's now an inhomogeneous polynomial in two variables. So fi so in general it will be inhomogeneous in two variables. And obviously these constructions are inverse to each other, in the sense as long as you restrict to the case where z does not divide fh. Of course, if we have z as a factor of f, then this will be completely forgotten because we set z equal to 0. But if this is not the case, so if we restrict to the case that z does not divide f, then the degree will even be the same as before, and we have a one-to-one correspondence between the homogeneous polynomials and the inhomogeneous ones. So this gives a bijective correspondence between, so on the one hand side we have polynomials of degree d in kxy in two variables, and on the other hand we have homogeneous polynomials of degree d in three variables that don't contain z as a factor. On that side we would have homogeneous polynomials of degree d now in three variables that don't divide z. The operations are, of course, the ones up there. And so if we have a polynomial, you can make it homogeneous to go to the right side, and if you have homogeneous one, you can make it inhomogeneous to go to the left. So that's the one-to-one correspondence. And of course, the geometric interpretation of that is setting z equal to 1, or in the original language, x0 equal to 1, just means that you restrict to the affine part of projective space and forget the points at infinity. And that leads to the definition, even like for curves, so that means for polynomials modulo scalars, what the affine part and what as it's usually called projective closure, or the projectivization of the curve should be, namely just given by these operations on polynomials. Yeah. Let's do the construction. in the considering affine parts and projective closures of curves, which is essentially the same thing, just if you consider these objects to be curves instead of polynomials. Then the part A, so maybe start from a projective curve. So if capital F is a projective curve, then if we take its projective set of points, so Vp of F, and intersect it with the affine plane, so A2, then that was given by all the points where we set z equal to 1, or like the x0 coordinate being to 1. So that means that is the affine zero locus actually of the inhomogeneous part of F, considered as a subset of A2, just by what this A2 is. And that's why we also, on the level of curves, so on the level of polynomials, want to call this Fi the affine part of the projective curve F. Hence, we call the affine curve Fi the affine part of capital F. And so it will be obviously then an affine curve. The other way around, if we start with an affine curve, so if capital F is an affine curve, so meaning in two variables, and possibly inhomogeneous polynomial, then we do the opposite thing. So then we define its projective closure to be the homogenization, to be as a curve to be FH, and that by this construction is a projective curve whose affine part is again back F, and that doesn't have the line at infinity as a component. So that's, I guess, what the name projective closure suggests. I mean, we make it into a curve, so we add some points at infinity, but we don't add the whole line at infinity. So it is a projective curve then, obviously, whose affine part is back F. And that doesn't have Z as a component. So the line at infinity. So that means the same operation that we had there, closure of homogenization and dehomogenization on the level of polynomials has a geometric interpretation of taking only the affine part of curves or of a projective curve, or if we start with an affine curve, to make it into a projective one by maybe adding some points, but not the whole line at infinity. In fact, we can say a little, about which points we add, because that's, see this quite easily from the polynomial. Let's do that. So if we have so for the second part B here, if we have an arbitrary polynomial which is not homogeneous, so say more precisely, well, let's not say it that way. So I want to say it doesn't have Z as a component, but let me say it this way, it may have points at infinity. Because, so say if we split this into its homogeneous parts, so F0, F1 up to Fd, where d is the degree of F, then of course its homogenization is given by adding a z to the d here and d minus 1 here and so on, and no z here. So it would be z to the d F0 plus z d minus 1 F1 plus and so on, and the last is z to the 0 Fd. So that would be the homogeneous polynomial that gives back this thing. And if we now take the line at infinity, which is given by z equals 0, then we set z equals 0 here, and the only thing that remains is the last one. So points at infinity are, meaning like you intersect V of f h of the homogeneous part with the zero locus of z, so with the line at infinity. Then if you take z equals 0, well, you get only the last one. So that would be the projective zero locus of only fd, and of the leading term, as a subset here of p1 in the two coordinates. So that's all projective zero. So that means in the similar way as in the affine case, the first non-trivial term here would give you some local information about like the singularity at a point at the origin. The last term, or the leading term, the highest term, would give you some information about the points at infinity. And which should also be sort of intuitively clear, because for small values of the coordinates, like it's the first terms that are relevant, and for large values, if you go towards infinity, then it's the highest terms that are relevant. And that's exactly what happens here. So we can, in fact, look at examples there to see what this looks like. Namely, if we want to visualize these curves, then we saw that like even the real projective plane is a bit weird to draw. I mean, you cannot embed it in R3. But what we can do is, draw the affine part and then maybe just indicate what the points at infinity are. So maybe as an example or remark, say to visualize projective curves, if you want to draw them, we might draw the affine part. That's one possibility to do that. We can draw the affine part, so Fi, and indicate the point at infinity that we add by their directions. And what this might be, so let's consider a few concrete examples, is namely for conics. That would also cover maybe the case that we have in the homework. That might look as follows. There's various ways over the real numbers. So of course, this visualization is mostly over the real numbers. There's various ways what the zero loci of quadratic curves might look like. Maybe right here over R. That's the main case I'm thinking of if we want to draw pictures. So let's start maybe with something like a hyperbola. So take so the affine curve. You might take so xy minus 1. So that's where we know what it looks like. Maybe that would be something like that. Y is 1 over x. So that's the affine picture that we would draw. Now in our projective setting, we would say the projective closure is given by, this is make homogeneous by an additional coordinate. So that would be xy minus z squared. So that would be the corresponding projective curve. And that consists of this affine part. So that is again the affine part of the projective curves. But we have added some points at infinity. And the points at infinity are given by considering, either we start here and say we only take the terms of highest degree, which are x times y, or which is the same, saying just setting z equals 0 here, which is again x times y. And x times y has its two directions, namely the two axes, and we might draw those as additional axes. Either you draw it somehow that these are axes in the sense that they are asymptotes to the curve, or you think of it that there's a point sitting at infinity in both in this direction and in that direction. which I think is both geometrically imaginable that this is what happens. So there's 2 points, so both of these dashed lines stand for 1 point at infinity, and that's what the projective closure looks like. We add 2 points. If we have other cases of conics, I mean, we might have the case that we have a parabola like y minus x squared, where standard picture is like this. Then the projective closure here would be, we make this homogeneous by another coordinate. Make 1z here. That would be the homogeneous polynomial in 2 variables. And the points at infinity we get by setting z equal to 0. We just keep x squared. It's the same as here, the highest degree term. And x squared, no, only x is 0 gives a component, then that would be this one. So and that means in that case, you would have 1 point at infinity, which sits there at infinite distance on the vertical axis. And one last thing that we could consider might be a circle. So we have something like x squared plus y squared minus 1. Or ellipse or something similar, then the picture would be like that, the real picture. And if we consider the projective closure of that, that's x squared plus y squared minus z squared. And the points at infinity are given by setting this equal to 0. So we have x squared plus y squared only. And this has no solutions over the reals except for like 0, 0, which isn't a point in P1. So that means in that case, there's no points at infinity that we add, which also makes sense because, I mean, that doesn't go to infinity. Right? So that's just, again, like the idea that the highest order term should determine your behavior if we go to infinity. And so that means here we've added 2 points, here we've added 1 point, and here we've added no points. A nice thing to see is that, like, topologically, if you think of these curves, they become all the same. Because they are, I mean, this is a circle, and there we don't add anything, so this looks like a circle. But that topologically also looks like a circle, because we can come here and there, and then we have 1 point at infinity, so that means the thing here somehow at infinity connects to this 1 point at infinity, and then you can come back on the other side. That would also be a circle. And in the same way, that would be a circle, because you could start here at any point, go up here to infinity, go to the point at infinity, which is the same as the one down there, and then go along this part, and here go to infinity, and then that's the same as this point. And so we can run through this curve like a circle, as if we have completed it to projective space. So, I mean, that's more like an intuitive statement. And in fact, this one homework exercise that's on the current sheet says pretty much exactly that. I mean, that all smooth conics over the real numbers will become the same after considering its projectivization. Or just maybe write down, so note all these curves, these real projective curves, are topologically circles. So that would be an example over the real numbers here. And yeah, maybe so. Are there other questions for that? So the main point for today actually would pretty much be like going quickly, and I'll try to do it quickly through the chapters like 1 and 2 again. So the things that we did for affine curves, and see how they generalize, or how they adapt, how they can be transferred to the projective case. There's just one remark that I want to make before, and that's something that's really here unique to algebraic geometry in general. It's nothing that we would really follow in this class, but I think it's nice if we see it once. Namely, if we consider the space of all projective curves, say of a given degree, so space meaning the set, let me just write set, of all projective curves of degree d, is, so what is it? So a projective curve of degree d is given by a homogeneous degree d polynomial. So you would start with ax, y, z, d. So that should denote homogeneous degree d polynomials. But we don't want it to be a constant one, so we have to take out the 0, right? So that's without 0. And we identified any two polynomials if they are just differ by a unit. So that means we mod out an equivalence relation. We say that some f is equivalent to g if f is lambda g for some lambda in k without 0. And if you realize that this, as a vector space, this here is just a finite dimensional vector space of homogeneous degree d polynomials, this is exactly the construction of a projective space. Namely, as this here is isomorphic to k to the n for some suitable n, or let's just do it so that it looks really like the definition of a projective space in n plus 1. Where n plus 1 is the degree of this vector space, and you can check combinatorially what it is. I think it was d plus 2 choose 2 or something. Just whatever the dimension is of homogeneous degree d polynomials in two variables, then you would see that this is in fact isomorphic here to a projective space, again, Pn. Which means that the space of all projective curves here of a given degree d is in fact again a projective variety. So that is something that you could study using methods of algebraic geometry. I mean, not in this class because it's not a curve, so that n will usually be bigger than 2 or 3 because it's that number. But if you do algebraic geometry in general, then that would again be a space that you can study using algebraic geometry. So this is a projective variety again. So i.e., so let me put this in quotes here, like that the space of certain algebraic varieties is again a variety. So we've seen it here in the case of plane curves, but that's in fact true. So in pretty much generality in algebraic geometry, and that's a very unique feature actually of algebraic geometry. I think you have this in almost no other category. So if you think whatever you think, like if you think of groups, like if you take the space of all groups, doesn't have a group structure, right? The space of all vector spaces doesn't have a vector space structure. And whatever you could think of, it's usually not the case that the space of all objects of a certain category is again an element of that category. But here that's often true. And that's, as I said, a very unique feature in algebraic geometry, and actually a very powerful feature of algebraic geometry, so that if you want to study like families, sets of curves, that you can use the same theory as you use for the curves themselves. But as I said, we don't want to do it here because it's usually not a curve, so it falls out of the area of this class, but not out of the area of algebraic geometry. Yeah. But as I said, the main point for today would just be that carry over all the stuff from chapters 1 and 2. So now transfer chapters 1 and 2 to projective curves. So that means in chapter 1 there wasn't even that much. But chapter 2 contains all that stuff about multiplicities, intersection multiplicities, and multiplicities of points on curves, and there we should say something about it. As for chapter 1, let me just say it as a remark. So pretty much every statement that we had there, which weren't too many, carry over to the projective case. Namely, as for chapter 1, we have the following results. So they mean that also for projective curves, say capital F and G, it holds that. So what were the results? So the first that we started with was how many points we have on the curve, namely that, so maybe start with if the ground field is algebraically closed, then V of S was infinite. So if K algebraically closed, then the zero set is infinite. Let me just, for all these points, not just quickly say something about the proof. I mean, here it's very obvious because the affine part is already infinite and we just add points, so clearly it's still infinite. Now, if K is infinite, we had seen that the complement is infinite. So then P2 without V of F is infinite. Again, if we just restrict it to the affine part, then we see the complement of an affine curve, and that is infinite. And so we just add some more points. So that would still be true. Then we saw that the intersection of any two curves was finite as long as they don't contain a common component. So V of Fg is finite if F and G have no common component. So for this part, it's probably most useful to think of the projective space as being covered by three affine spaces, namely by first setting the first and then the second and the third coordinate to be non-zero. And in each of these three parts, you see affine curves. And if you have curves without common component, you would have finitely many points. And you have three patches. So at the end, you will have finitely many intersection points at most. And then there was this result of how to reproduce the curve from its set of points, namely if K is algebraically closed, then a curve F can be recovered from its set of points together with the multiplicity on each component. That means that the pictures that we draw actually adequately represent the curve that we want. We're recovered from V of F, or now Vp of F, of course, together with a multiplicity on each component. The only thing now is that there is one additional component, possibly, namely the line at infinity might be a component of the curve, but that's the only component that we could have. And then if we specify a multiplicity there as well, so usually I guess we'll restrict to curves that don't have the line at infinity as a component. Otherwise, we would change another line at infinity because that's a bit hard to draw. Well, then again, we have the same statement as before. So these were, I guess, the results from chapter 1 on curves, on affine curves, and that they still hold in the same way as before for projective curves as well. So the chapter 2 is clearly more interesting. So there we started with the intersection multiplicity. And there we should say, I mean, how that actually transfers to the projective case. And that's a little more involved than one would want it to be. We'll see in a minute why. So construction. So consider intersection multiplicities. So if you recall how we did this in the affine case, we had the local ring on the affine plane, and then modeled out the ideal by the two curves and considered its dimension as a K vector space, and that was the multiplicity. So let's start that with the local ring, and for that we do the following. So first construct local rings. As follows. So for for P, a point in P2, and if we need it, we might call the coordinate x0, y0, z0 maybe a certain point. We define the local ring of P2 at P to be the following. So the notation would be then OP2 comma P, or just OP. That's the same notation as we had in the affine case. And the construction is quite similar. So we take quotients f over g of polynomials such that the denominator doesn't vanish at the point. Just, of course, the idea was that this describes local functions at the point. And now we had seen that unless we make these polynomials homogeneous, they will not define functions. And we even have to make them homogeneous of the same degree, otherwise they wouldn't define functions on the thing. So if that should be the ring of functions locally around the point P on P2, we would have to make them homogeneous of the same degree, and that's actually what we require here. Namely, f and g are polynomials in 3 variables, x, y, z. They should be homogeneous of the same degree. And of course, the denominator still shouldn't vanish at the point p. P is not equal to 0. And that we consider as a subring of the ordinary ring of, or the field of the function field k, x, y, z. Or that would be the field where everything lives in, like the field of quotients of polynomials in 3 variables. And it's just a subring of that. And there we would define to be the local ring. So the idea, as I said, is just they should define functions locally around the point, and that seems to do it. As before, as in the affine case, we do then have an evaluation map at the point P. Namely, we can now plug in a point P, get a well-defined function at the point P. With this definition, we have an evaluation morphism. It's like a ring homomorphism. Namely from OP to K. Which is evaluation at P. So that means we send f over g to f at P over d of P. And the kernel will again be, as it was in the affine case, which we call an IP or IP2 comma P. It's the same thing as here, just that we have that the numerator also vanishes at the point. So we have f over g. Again, they would be homogeneous of the same degree. So means same but not fixed degree, right? So different elements could have different degrees on the top and on the bottom, but they must be the same for each element. And then, of course, we still have g of p not equal to 0, but f of p is equal to 0. So that is the corresponding definition in the projective case. And the nice thing about this, and that's how it's done, is that if we restrict to a certain affine part, maybe say the standard affine part where this is 1, the last coordinate, then this would actually be an isomorphic ring to the one that we got in the affine case. So if we take such an element here and set z equal to 1 in both polynomials, then we get an ordinary quotient of 2 polynomials in 2 variables, which are not necessarily homogeneous anymore, but where the denominator still doesn't vanish at the point. And that gives rise to an isomorphism of rings, of these local rings, namely of this local ring with the corresponding affine local ring if we set the last coordinate equal to 1. So that's how this is constructed. And we can get all the affine local rings from that one. So then note, there is a ring homomorphism, actually isomorphism. If v0 equals 1. So if we are in that affine case, namely from O P2, P, well, we write out what the point is, so x0, y0, z0, 2O of A2, so the definition in chapter 2, at the point x0, comma y0, which is just given by taking exactly those polynomials and setting z equal to 1. That means you just take the inhomogeneous thing. So you send f over g to fi over gi. And of course, the map the other way around would be homogenization of the same polynomials. And making it the same degree. So possibly you have to add another power of z. So that would be a ring isomorphism. And that actually does take this ideal to the other ideal. And that tells you, I mean, if you know, in the other case we had seen even algebraically, it's a local ring. So that means that would also be a local ring. I mean, it's the same, it's isomorphic to the other one. And again, this would be the maximal ideal. And this OP2P is again also algebraically, but if you know what that means, a local ring with maximal ideal IP. So up to that point, it looks pretty much the same as in the affine case. The slight problem with that is if we now want to define the intersection multiplicity, would want to write down something like OP modulo f comma g, the ideal generated by f and g. But f and g are not even elements in that. Because for the elements in there, we need quotients of homogeneous polynomials of the same degree. In particular, a homogeneous polynomial would not be an element in there. So at least at first, we cannot write down something like OP modulo ideal generated by f comma g. But what we can do is still, I mean, there's a corresponding thing to the ideal generated by f and g, namely that we take any linear combination of f and g, where the coefficients are things like that, f over g, where the degrees are exactly so that this matches up, and that we get the same degree in the numerator and the denominator. And that's the construction of intersection multiplicities. Oh, it's still the same construction. So that was more like local rings. So they now go to the intersection. Now for the intersection multiplicities. So note that polynomials, or like in general, like the polynomial ring kxyz is not a subring of this thing. Of OP. So the question is, so what is something like the ideal generated by fg or fg homogeneous polynomials? And as I said, so you want to take pretty much the same formula as you take for the ideal generated by this thing in a commutative ring, namely just linear combinations of that. And the coefficients should be things like that, so that the total degree becomes 0. Namely, so for that we define I don't know if we might need ever more than 2 generators, so an arbitrary number of generators. So let's keep that variable. So for f1 up to fk, and kxyz homogeneous. So not necessarily all of the same degree, but they are all homogeneous. Then we define something that we write in the same way as if it was the ideal generated by these things. And it's the set of all linear combinations. In fact, it will be an ideal, just at the moment. So f1 over g1, capital F1 plus, and so on, fk over gk, capital Fk. Where again all the f and g are homogeneous. All the g's are non-zero at the point P, but the degree of the little f and little g are not the same, but they are just so that the degree of little f times capital F is the same as that of g. And that would make this expression lie in this OP, and then we're fine and have defined an ideal in that. That means all the fi and gi are homogeneous. We have gi of p not equal 0 for all I. And we have that the degree of fi, so little fi, capital Fi, is the same as the degree of gi for all I. Then this thing will lie in OP, and that's what we mean by that expression. That sits inside OP and is, in fact, that's easy to check then, is in fact an ideal. So maybe the most interesting property, if you multiply it again with a thing of that form, it would still be of that form, right? Because then you multiply each term with a polynomial on the top and at the bottom, but they are both homogeneous of the same degree, so that would still hold. So that is in fact an ideal. And with that somehow new definition of the ideal generated by that, we can then still just copy what we did before and define the intersection multiplicity to be the dimension of OP modulo this ideal generated by F and G. To say with this notation, we then define UP of F comma G to be the dimension as a K vector space of OP mod FG, right? With FG in the sense defined up there. You should note that you will probably never compute it that way. That's just to make sure it's well defined and doesn't depend on any choice of coordinates. To compute it, you would again want to pass to an affine patch, right? So that means if we restrict, say, to a point where z0 is equal to 1, then you can transform to the affine local ring to that one and then take the corresponding polynomial set z equal to 1 and compute the affine multiplicity there. So to compute it, we pass to the affine case. Namely, if in the point what we call it x0, y0, z0, so if z0 is equal to 1, then we have this isomorphism between the rings. Like from, what was it? Somewhere up there. And this isomorphism, it's easily checked. I mean, it maps this Fg to F inhomogeneous and G inhomogeneous. So the isomorphism that we had up there, so OP2, and then the point P, so x0, y0, z0, to OA2, x0, y0, maps the point, the ideal, okay. Fg to F inhomogeneous, G inhomogeneous. Quite clear by construction. So that means our mu P that we want to compute Fg in the projective case would be a mu at the point x0, y0 of F inhomogeneous and G inhomogeneous. And so that's the affine case here on the right hand side. So, and there, of course, we know how to compute it. So we had an explicit algorithm for that. And then we could do that. So that would be in the case if z0 equals 1, but if it's not, then we just use the trick that we take any other coordinate, which is 1, which is non-zero, and then we can set equal to 1 and do it in that case. For points at infinity, or for points, we'll write it that way. For points where z0 equals 0, we use a different coordinate as line as infinity. So let's maybe do an example where you could see that, where we compute the intersection multiplicity even at an infinite point, at least if we do it in the standard choice of coordinates. And we take the parabola that we had as one of our examples earlier and intersect it maybe with the line at infinity, which we cannot really draw. It would be the set of all infinite points. So it's somehow like a big circle around the whole picture. For example, so let's say our curve f is again. So we take again our curve xy minus, no, it's not xy minus e squared, it's yz minus x squared. So that was the thing that in the affine coordinates y minus x squared is the parabola. What was that thing? In xy coordinates, and then we said that there's like an additional point at infinity up there, which we could draw like with a dashed line or something. And that's the point that we want to consider actually. So P that has the coordinate 0, 1, 0. So it has the z coordinate 0 and it's the direction 0, 1. So it's the infinite point in that direction. And for the other curve G, we just take z, the line at infinity. So again, as I said, it's hard to draw, and in the notes I didn't even try. So it was like, I mean, if you think of this point at infinitely far away, then you could think of G as being like the set of all those infinite points here around the plane. And this curve somehow goes through this point at infinity. And there would be an intersection multiplicity there. And so the picture maybe suggests what the result should be. But at least we could try to compute. I mean, computing it algebraically is no problem. So if you take mu p fd, so mu at the point 0, 1, 0 of yz minus x squared and z, then we have to take a line at infinity. So we shouldn't take this line at infinity. Then we couldn't compute it using the affine case, but we can compute the affine patch where y is equal to 1. I mean, it's the only choice that we have, right? So y is equal to 1. So that means here we take the affine part with y being the line at infinity. And what this means is that the dehomogenization is not done with respect to the variable z, but with respect to the variable y. So that means we set y equal to 1, which is already the case. So that means we end up with the origin 0, 0. So the zeros are just those two coordinates here. And for the polynomials, we have to set now y equal to 1. And that gives us z minus x squared with z. And that's now an affine intersection multiplicity that we can easily compute. For example, because we see that we can subtract z from here. So we get x squared z, and that would be 2. So that means that we would say that we would want to say, and we will say it in a minute, that this line at infinity in the old coordinates, this g, is actually tangent to the curve at this point, which you might guess from the picture. And actually, if you would draw like the topological picture, so like the real projective plane as a manifold somehow, and look at this locally around this point, you would see the tangency actually. You just don't see it if you draw the affine picture with the point at infinity. Yeah. So that would be an example how to do intersection multiplicities. Yeah. All right. Are there questions there? Great. Then, well, that in fact is the idea, like to transfer everything, like to transfer to the affine case by using an affine patch. And as we can cover P2 by these affine spaces, this actually applies to any possible point. And that's probably the easiest way to define all the concepts of multiplicities of points and smoothness and all that for projective curves, namely by just passing it to the affine case with any possible choice of coordinate at infinity. So, so let's do that. So another construction or definition or whatever I call it. Here, construction. So leading to notions of multiplicities of points. And tangents and smoothness. So this is done again by taking the affine part, and hence we might restrict to the case where the last coordinate is equal to 1 or non-zero. So we can take without loss of generality a point with last coordinate non-zero, which we can set equal to 1. So if not, take another coordinate. A point P as above, x0, y0, z0, z0 equal to 1. So otherwise, use a different coordinate for the line at infinity. And then we just copy all our definitions, right? For example, the multiplicity at a point, we define multiplicity of P, so at the point P, on a curve, projective curve F. As MP of F to be M at the point where we go into the affine case, so we write it x0, y0, so the corresponding affine point, and then add of the corresponding inhomogeneous polynomial. So that would be the obvious choice. Now, in the same way, we could define tangents, and we would take the tangent of the affine curve then in that, and take the projective closure. So a tangent to f at P, that is the multiplicity. Tangent to f at P is the projective closure of a tangent to fi at the point x0, y0. And in the unique case, so if we are if there's exactly one tangent, because this multiplicity is 1, we would again denote it TPF. Denote by TPF if MP of F is equal to 1, so that the tangent is unique. Then in the same definition was like the words of smoothness and singular points otherwise, and we just copy that as well. So if this multiplicity is 1, we would call it a smooth point, and otherwise a singular point. So that means the computation, just if you do it by definition or by construction, would be passed to an affine part and computed there using the old methods. And if you want the tangents, then you would have to take the projective closure of the line that we computed. Yeah. That would again be something that would have to be checked, right? I mean, that you mean that if he Even if you take something, if you have a point where you have two different coordinates that are non-zero and use the one or the other, yeah, that would actually have to be checked, yeah, by computations. I guess you would have to consider the transformation from one. First of all, you just move to the, yeah, okay. Otherwise, it wouldn't even be the 0 point probably in both coordinates, right? So I guess you would have to write down the explicit transformation from one set of variables to the other, which you could do, I guess. So if you go from the x0 to, say, the x0 z0 case, so one is obtained by setting z equal to 0, the other by setting y equal to 0. But you can somehow pass from one to the other and see what the terms are. Yeah, that would probably involve some computation, I guess. I agree that this doesn't look overly natural. If you say take any one of them, but I would expect that you could do it in a similar way to that. It's just that the thing with already with the definition here of in the affine case, we had this somewhat construction, well, in the origin is that, and otherwise shifted to that, which wasn't maybe overly natural. In fact, for the case of, if you just want to know if it's a singular point or not, we will see just in a minute a way that will tell you that. But if you want to see that the multiplicity is actually the same, I guess you would have to write down the transformation from one. You have just to make the coordinate chains explicit and check what happens. But as I say, for smoothness, which we want to define now, we just right afterwards a proposition, namely the Jacobi criterion, essentially, that works in a similar way in projective space. And that does not depend on a particular choice of coordinates. So there you see it. So we maybe write down this definition, namely point. So P and F is called smooth if MP of F is 1, otherwise singular. With the variance in the same way as we had it for affine curves. So instead of smooth, sometimes you say regular, and the whole curve F is called smooth if every point is smooth. If all P and F are smooth. Yeah. So that would at least be the definition. Modulo maybe be that part that you would have to check the coordinate transformation. So I guess these were all the concepts that we had regarding to that point. And then we said, in order to compute this in the affine case, we had this one, as I said, the criterion, namely the Jacobi criterion. And there's actually the nice point, and that's one thing I want to do, because that's what you usually do if you deal with projective curves and want to check smoothness, that this also holds an inversion in the projective setting where you don't have to split up onto the affine coordinates. So, in fact, we want to show that the Jacobi criterion for smoothness has a projective version for which we don't have to consider affine parts. And that's in fact something that you see in projective geometry all over the place. So I guess the just like a moral remark, so to say, what you do in algebraic geometry a lot is in the same way as when you consider manifolds in analysis, is that you want to patch affine varieties together to bigger spaces. So to consider spaces that locally look like affine varieties, and in the same way as a manifold would locally look like an R to the n analytically. And Then, of course, if you want to prove anything about these objects, you always have to go to these local patches and compute your stuff. But projective varieties, I mean, they are of this type. I mean, they are covered by affine patches, so they are kind of manifolds in that sense. But they pretty much always have a way to deal with them without passing to these patches if you actually want to compute something. And we did it here in some parts, namely for the intersection multiplicity. I gave you the construction of the local ring in P2, which was a slightly adapted definition, but it holds then for all the points and not just the affine part. And well, here I didn't, but I guess one could do that probably as well. And for the projective, for the Jacobi criterion, that works as well. And for that, we need one lemma actually before, which you might have seen before, namely it's in just a lemma on homogeneous polynomials. And it says for all f, say, do it in 3 variables, but actually it doesn't matter, homogeneous of degree d. We have that if we take the partial derivative df by dx, multiply it with x, and do this for all the coordinates, so y times df by dy plus z times df by dz, we get back f up to a factor, which is just the degree of the polynomial. We'll just need that in the criterion in a minute. And so the proof is actually very simple. It's just computation. So we say our polynomials of the form sum over ai jk xi y j z to the k, and the sum I plus j plus k is equal to d because we're a homogeneous polynomial, and then we just compute that. Right? So namely, if you take x times df by dx, then you have the standard rules for derivations. So you take here, so the coefficients will carry over ai jk. So then we have the exponent, which is I, and then times x to the I minus 1, but we multiply again with x, so it's actually not I minus 1, or it's I minus 1 plus 1 times y to the j times z to the d. And that means it's just the same term here, not d, okay. It's just the same term here, just that we have an I in the sum. And of course, that holds similarly for the others. They will give a j and a k. And if we sum them all up, the 3 terms, then we get an I plus j plus k in the sum, and that's always d. We have a homogeneous polynomial, and that we can pull out of the sum, and we just get d times f. So that's a really very simple computation. Maybe you've seen that before somewhere. But then we need to carry over the Jacobi criterion, which needs these derivatives. So hence that means if you compute x df by dx plus y df by dy plus z df by dz, then we get the same sum over all I plus j plus k equals to d, and then the I jk, and then I plus j plus k times y to the j, d to the k. That is always d, all we get as a total d times f. So that's and that's Bobby, but it is sort of the main thing that we need for the projective Jacobi criterion. And so formulate that as a proposition. And it's really totally analogous to the affine case. That's a nice thing. Namely, so say that P be a point on a curve f, namely a projective curve now. Then part A was, so the affine criterion part A said P is a singular point if and only if both partial derivatives are 0. And the same holds here just for all three partial derivatives. And P is a singular point if and only if df by dx and df by dy and df by dz all at the point are 0. And from that formulation, for example, you would see that it doesn't depend on the choice of coordinates. B, so part B of the affine-Jacobi criterion was if it's a smooth point, well, then it has a unique tangent, and we could actually say what the tangent is, and the same is true here. So if P is a smooth point, then the tangent TPF is given by, and if you recall, the affine result was we have the partial derivatives, that we only had two, as coefficients in front of x minus x0 and y minus y0. And here it looks very similar, and namely it is df, all the partial derivatives, df by dx at p just times x, and then you do this all three. So df by dy p times y plus df by dz p times z. And of course, no constant terms. I mean, we do need a homogeneous polynomial. That's a homogeneous linear polynomial. But it's as close to the affine formula as it could get. And that's, I guess, the criterion that we will usually use. Then we don't have to pass to any affine patches. And that would give you the result right away. The proof, of course, is done by the affine case. So that means we pass to an affine patch and check it there. For that, we can reduce to the case where the 0 is 1. And we do that actually for both parts. So, proof. So that say P be the point x0, y0, z0, and again without loss of generality, set z0 equal to 1. Because the result clearly is symmetric in the coordinates, so we could just take any for that. Well, for A now we just saw, of course, in general we use the affine-Jacobi criterion. For the inhomogeneous part, Fi. Then, for part A, you would say that P is a smooth point. If and only if, so we have defined it here by saying pass to the affine patch and check if it's a smooth point there. So it would be the same as saying x0, y0 is a smooth point of Fi. That was our definition. And for that we use affine-Jacobi, right? So that we know is the same as saying if we take dfi by dx at this point, x0, y0. Oh, I said smooth. It's better to say singular probably. Because then we can say they're both 0. So say it's a singular point here, only if it's a singular point here. And that is the same as saying both partial derivatives at the point x0, y is equal to 0. Right? So that's affine-Jacobi. Now how does that compare to our partial derivatives here? So what do we do here? We take inhomogeneous part, which means we set z equal to 1, and then we take partial derivatives. Right? That's what we have here. But of course we know, I mean, that does hold in analysis, but it also holds for formal differentiation of polynomials with respect to several variables, that differentiation with respect to one variable and setting a variable equal to a value in another variable just commutes. Right? It doesn't matter how you doesn't depend how you do that. So that means you could equally well first take the derivative of the original polynomial and then set z equal to 0, you would get equal to 1, you would get the same result. And that in our notation is you take the original polynomial and you take the derivative with respect to x, and then you evaluate this at the point x0, y0, 1. And you just commute evaluation with differentiation with respect to different variables. And that really works. So here we have f dy x0, y0, 1 is equal to 0, and that is the point P, and that is the point P, and so that gives us exactly the first two here. So it looks as if we had here only df by dx P is equal df by dy P equals 0. And that's actually true, because the lemma, I mean, here we have also df by dz, and here we have only 2. But the lemma before tells us that that's actually the same, because we have a point on the curve. That means f of p is 0. So if we plug in the point P, and this is 0, and then if we are in the case that these two are 0, then that would have to be 0 as well. That's just the lemma. Right? So the lemma together with the observation that f of p is 0, so the right-hand side would vanish. The lemma with f of p is 0 would tell you that this is equivalent to the case where you have all variables in here. And that is part A of the thing. And in fact, it is, I mean, that's now where it's important here, this without loss of generality. Of course, if you had a different variable being 1, then you would end up with 2 different variables. So in fact, in the really general case, you would need all 3. But if you are in that affine part, the 2 of them would be sufficient. That's because of this relation here between the polynomials. Let's show part B as well. For that, we also had a formula in the affine case, what the tangent is, the affine tangent. Let's use that, right? So B, again, by affine Jacob. The affine tangent is the following. Namely, the formula there was, I mean, it had originally those parts, the inhomogeneous by x at the point, but we've seen already that they are the same, right? So I can just use that expression. It was df by dx p, and then times x minus x0 plus df by dy y minus y0, right? Set, at the point p times y minus y. So that was the formula in the affine Jacobi, and originally, as I said, with these derivatives. Anyway, well, that's an inhomogeneous polynomial, of course. So maybe let's split the homogeneous and the inhomogeneous parts. So that would be the same, or like the linear or the constant parts. So that would be df by dx at p times x only, plus df by dy at p times y only, and then we have the minus x0 minus y0 part. So that is minus x0, or say it that way, 0 df by dx at the point p plus y0 df by dy at the point p. So that is a constant here, right? On the right-hand side. It doesn't depend on any variable. And for that, we use again the lemma. Right? So this is an expression exactly of the form as we have there. So x times derivative at the point plus y times derivative at the point. So by the lemma, this would be f at the point minus z times derivative with respect to z at the point. But f at the point is again 0. We're on the curve. So that is by the lemma would be d times f at the point, that is 0, and then minus d0 times df over d0 at the point p, but d0 is 1. So that means the expression that we have here, so the double minus will cancel, and we have the dx f by dxp times x plus df by dy p times y, and then we have a plus df by dzp times 1. So that vanishes, that's 1. So that's still the affine tangent, and now we define the projective one is the projective closure of that. And the projective closure means make this homogeneous by the variable z. And so here's a linear term, here's a linear term, here's a constant term, so we have to add the z here to make it homogeneous. So then we take the projective closure to obtain the actual tangent TPF, and then we get again the desired really symmetric form in all the variables for df by dxp times x plus df by dyp times y plus df by dzp times z. And that's the expression which is symmetric again in the coordinates. Yeah. There's just two things I want to do. Are there any questions? Otherwise, there's just two things I want to do at the end, and for that, what I want to keep maybe this lemma here. So we've used this lemma now again, like twice, to compute one of the terms in terms of the others. And it was always in the direction that, well, if we have a point on the curve, then this is 0. And then we expressed one of the three terms in terms of the others. You could also do it differently, namely if we know already that all these three partial derivatives are 0, as it is in part A, then the lemma would tell you that the point actually does lie on the curve, at least unless d is 0 in your field. So if you have a weird field where d might be 0, then this is not true. But if we do it, say, over the say, for example, over the reals or the complex or anything of characteristic 0, then this will not happen. And we can, in fact, make the projective Jacobi criterion a little nicer in the sense that we don't have to require initially that the point is even on the curve. It will figure that out for you. So if it spits out a singular point where all the partial derivatives are 0, it will be on the curve. So that's the remark. So if the characteristic of your ground field is 0, or it's not the divisor of d, that would be sufficient. If the characteristic of the ground field is 0, then by the lemma, the partial derivatives being 0 at a point equal, and maybe if you take all three of them, implies that d times f at the point p is 0, and if the characteristic is 0, that means that f of p. So that means that, hence, to compute singular points, we don't have to require. Now I erased the Jacobi criterion, but it started by saying let P be a point on F. And actually you could replace that, let P be a point on P2, which is a weaker assumption. You don't have to check P in P2 at the beginning. We don't have to check P and F. Right? P and P2 is sufficient. We don't have to check P and F. At the beginning, right? That makes it nice, and that's the way we usually use the Jacobi, the projective Jacobi criterion. If you have so I can do an example next time because the time is up now. If you start with a homogeneous polynomial, what you usually would do is just compute all three partial derivatives, compute their common 0 locus, And if there is none, then there's no singular point. And if there is one, then you will have computed a point on the curve, and then it will be a singular point. But as I said, it's an example we could do next time, and then go on with the study. So then we've actually caught up with like transferring the affine results to the projective results, and we can start doing new things, which would be like computing numbers of intersections. That's what we do then next. Right, so if there's no more question, then we'll just end here and continue next week. So next week is still no holiday on this day at least, so that will be fine. All right.